Welcome back. We recently showed that there are no circuit loops for the 3n+1 problem, but we had to use some heavy artillery from Alan Baker, which we don't even know how it works. So today we're going to try to prove the same thing, but with our own little sniper rifle instead of Baker's heavy artillery. Okay, every circuit loop of length k has some number of up moves in yellow and some number of down moves in blue. And we want to know if the values along this loop are integers. The bottom of any circuit loop, m, is given by this formula. So if m is an integer, we have a valid circuit. For example, here's the loop with 3 ups and 2 downs, and the bottom of this loop is 19/5, not an integer. And we want to show that m is never an integer, no matter how many yellow or blue blocks we want to use. So we showed before that there's a greatest common factor between the two things we care about. And if this is really a multiple of that, then that's got to equal that greatest common factor. And we also found through simple addition that the greatest common factor of these two things is the same as the greatest common factor between these two things, which means for a valid circuit loop, then 2 to the k minus x minus 1 also has to be a multiple of that. But 2 to the k minus x minus 1 is so small. Here's a chart for various values of k and x, and you can see that this seems to be way bigger than that. But we have to prove that it's always bigger. And if we can do that, that can't be a multiple of this, then we've shown that there are no valid circuit loops. So to prove this, we're basically asking how close 2 to the k can get to 3 to the x. And Baker gives a very strong separation. Here, the difference between the powers of 2 and 3 get very large very quickly. And that difference completely obliterates 2 to the k minus x minus 1. Okay, here's a self-contained alternative. Just a few easy steps. Remember, there's k blocks, x is the number of yellow blocks, and k minus x is the number of blue blocks. We can factor this into two pieces, a sum and a difference. So the product is obviously bigger than the first term, and this sum is obviously bigger than its first term. Amazingly, not only is this whole thing here bigger than 2 to the k minus x minus 1, even just this tiny part of it is. That's because the number of blue blocks, k minus x, is less than half of the total number of blocks, k over 2. In a valid integer circuit, we need more yellow blocks than blue ones, otherwise we'll wind up lower than where we started. Remember, if a store increases prices by 50% one day, then decreases them by 50% the next day, the price goes down. So we need more price increases than decreases for the price to eventually return to its original value. So 2 to the k over 2 is our little sniper rifle. It's bigger than 2 to the k minus x, but just enough. And if we go back to our chart, you can see how it does its job. Okay, does that mean we proved that no circuit loops exist? Almost. The proof only works if k and x are both even. So an even number of yellow blocks and an even number of blue blocks. For example, take 2 to the 10th minus 3 to the 6th, which is 295. 10 and 6 are both even. If we factor this, we get 2 to the 5th plus 3 to the 3rd times 2 to the 5th minus 3 to the 3rd, which is 59 times 5. That product is obviously bigger than 59 itself, and this sum is obviously bigger than 32 by itself. So 295 is bigger than 32, but 32 is enough to do the job because it's bigger than 2 to the k minus x minus 1, which is 15. Thanks, sniper rifle. But if k or x is odd, it doesn't work. For example, take 2 to the 8th minus 3 to the 5th equals 13. Here 5 is odd. If we factor this, we get 2 to the 4th minus 3 to the 2.5 times 2 to the 4th plus 3 to the 2.5, or 31.6 times 0.4. This time the product, only 13, isn't bigger than 31.6. And that's because we have fractional exponents, so these terms aren't integers anymore. 3 to the 2.5 gets so close to 2 to the 4th that the difference term is less than 1. Anyway, this proof won't go through. But that's okay. It works when k and x are both even, which means we have 1/4 of an airtight proof that there are no circuits, without using the heavy artillery that we don't understand. Okay, so let's go from here to solving the 3n+1 problem.